nanohub.org.
Online simulation and more for nanotechnology.
Okay, so hello everyone. I'm Mark Lundstrom, and I'm going to be talking today about how we understand the physics of these very small transistors we're making these days. And before I begin, I'd like to thank Rodolfo for inviting me to give this presentation to the IEEE Mini Colloquium in Mexico City, and for permitting me to do it this way, since I'll be home giving a final exam while you're having this colloquium. Now, let me also point out that I'm doing this in front of a live class, so this is a good opportunity for me to wrap up the course on semiconductor physics that I've been teaching this semester. And what I hope you'll get out of this lecture is an understanding that these very small transistors that we're building these days are relatively easy to understand. They're not so complicated. So if you're an engineer working on it, I hope you find it useful. If you're someone who teaches this material, I hope you decide that this is the way it should be taught. It's not yet in the textbooks. Okay, so let's dive into it. So who is this fellow Lilienfeld? Some of my students think I'm old enough that I knew him. Actually, I don't. But he patented, this idea of a field effect transistor it's a reasonable thing to do. Back in the early 20s, when people were just developing vacuum tube technology, people came up with this idea that this would be a good way to make a transistor. Two contacts and a gate field. This is actually a MOSFET. It's not a MOSFET, but he patented a MOSFET a little bit later. Now, I'm told when I read, go on Wikipedia and read the history of the transistors, that they were never able to build any of these. And that's why vacuum tubes became the main electronic device for a long time. Actually, I'm not so sure that's true, so let me tell you a little story. I was basically saying this many years ago when I was teaching EE 305, or beginning semiconductor course here at Purdue. And I said, well, it's a nice idea, too bad they couldn't build it. And then after class, a student came up to me and he said, what do you mean they couldn't build them? I said, well, that's my understanding. He said, well, I live in California. I forget where. He said, my neighbor is a fellow named Heil. He's an old German fellow. And he tells me they work just fine. But apparently they didn't work fine enough to beat out vacuum tubes. And this was the transistor that Bell Labs tried to make after World War II because of all the problems with vacuum tubes consuming too much power and burning out all the time. They didn't make it. Actually, they tried to patent the concept, and somebody pointed out it's been patented long ago. They stumbled across this bipolar transistor just by accident, and that became the first practical device. But a few years later, Bell Labs did succeed. They learned that if you oxidize silicon and passivate the dangling bonds, you can actually make one of these devices. And this fellow Atala and Doan Khan made the first one in 1959, and they've just gotten better and better and better ever since, and it's really created the modern world that we know. Today we're making 22 nanometer transistors. This is the cross-section of a FinFET, the latest device incarnation, not a planar device, but where the channel is actually a thin fin of silicon, and the gate wraps around the fin to try to control the two-dimensional electrostatics a little bit better. So we've gone a long ways. And the point of all of this is to try to understand how these devices work. Just to calibrate you, in some history, so that students understand how rapidly things change. Before you know, you'll be my age and you'll look back on how crude things were when you were in school. My first job was to do N-channel MOS process development for Hewlett-Packard. I started in 1974. We made a 5-micron process. 5 microns is 5,000 nanometers. This was really state-of-the-art at the time. It was really difficult to do. All of the things that are in textbooks now we were discovering for the first time. And we ended up doing it. This is a plot of Moore's law, which is the number of transistors per chip as a function of time. Here's my first job. And if you plot this on a log plot, it's been doubling every technology generation for 40 or 50 years, and it will go for a few more. And each technology generation doubles the number of transistors on a chip, which is a measure of the power of the electronic system. So every time it doubles, you double everything you've done for the previous 50 years. So the implications are really enormous, and we don't know how far we can go. We'll probably get to 10 nanometers for sure. The question is, how far below 10 nanometers? The challenge is, can we get to 5? And how will those devices work? So we want to talk about how MOSFETs operate. Here's a simple circuit schematic for an N-channel enhancement mode MOSFET. Some of these devices have a 4th terminal. That's the body contact. Some of them don't, like a FinFET. And the basic idea is we apply a voltage between the drain and the source, and we apply a voltage between the gate and the source. The gate to source voltage controls the current that flows between the drain and the source, and we control the current, and we have a transistor. The IV characteristics look something like this. If you have a device that looks like that, you can make useful electronic devices. It has 2 regions of interest that we can focus on. One is a region of small drain voltage, where the current is proportional to voltage, looks like a resistor, but the value of the resistance is gate voltage dependent. The other region, the current tries to saturate. It doesn't quite saturate. The current here is more like a gate voltage dependent current source. It's more or less independent of the voltage across the 2 terminals, but its magnitude is determined by how much we put on the gate. So that's how a transistor operates. And the way we teach it in beginning semiconductor courses is very much the way people first did this in the 1960s and 70s and figured it all out, and it's still the way we think about transistors. I'm going to argue that it's not quite right anymore. They got a lot of things right, but they couldn't possibly foresee how far this would go. So let's look down in that low voltage regime. How do we think about the MOSFET IV characteristics? All right, it's very easy. We apply a gate voltage that's bigger than the threshold voltage. That induces a channel of N-type electrons. We get some negative charge in the channel. Charge is just capacitance times voltage, but we have to have at least the threshold voltage to get any significant charge. So we have that simple relation for the charge in the channel. So if I want to know what the current is, well, it's proportional to the width of the MOSFET coming out of the page. And then it's charge times velocity. More charge, more current. Faster the charge moves, more current. Okay. We know what the charge is. We just have to figure out what the velocity is. In this region, we apply a small voltage across the channel, highly conductive channel. The voltage just drops linearly. It's just like a resistor. The velocity is mobility times electric field. The electric field is just pointing from the drain to the source, so it's negative, and it's just the voltage across the 2 terminals divided by the length of the channel. Plug that all in, and we get this classic textbook expression for the IV characteristic of a MOSFET in the linear regime. All right. Easy to do. Okay, now if we apply a large voltage, we have to be a little more careful, because what we've been doing at low voltage is we say the velocity is proportional to the electric field. That works as long as the electric field is not too big. So one of the things we learn at the beginning of a course like this in semiconductor physics is that if you apply a very large electric field, the carriers get a lot of energy, they scatter a lot, and you just can't push them to go any faster. So the velocity saturates in silicon at 10 to the 7th centimeters per second. Okay. Now the question is, this occurs when the electric field is about 10 kilovolts per centimeter. How high are the electric fields in these nanoscale MOSFETs? Well, we have a drain voltage of about 1 volt. We have a channel length of roughly 20 nanometers. That's an electric field of 500,000 volts per centimeter. Right? 500 kilovolts per centimeter. So we're way out here. Right? The velocity should be totally saturated. Okay, so if we assume that it is, we can devise an expression for the current in the high drain voltage regime. So we'll assume the electric field is very big everywhere in the channel. Current is still proportional to charge times velocity. The charge at the beginning of the channel is minus Cox Vg minus Vt. The velocity is saturated everywhere because the electric field is big everywhere. So it's even easier than the first case. Nice simple expression for the current in the saturated regime. It just goes as proportional to the saturated velocity and proportional to Vg minus Vt. And if you see a transistor like this, and if you see the current increasing as Vg minus Vt to the first power, just linearly with the gate overdrive, the amount of voltage above the threshold, you say, aha, this is a velocity saturated MOSFET, right? So I know what I'm dealing with. Okay, all right, so these are the textbook expressions, all right? Everything is nice. Okay. All right, but let's look at the physics inside. One of the things that we spent a lot of time doing over the past 20 years or more is as the transistors get smaller and smaller, we have to go back and rethink the assumptions that we began with. And one of the assumptions is velocity mobility times electric field? Well, in these very small devices, we can do computer simulations. So these are computer simulations done at IBM in 1992. And in 1992, this is a 30 nanometer channel length MOSFET that was made. Nobody ever thought we would make 30 nanometer channel length MOSFETs. They thought, this is just some kind of academic exercise. Now we have them smaller in manufacturing. And every dot there is an electron that's being tracked through the device by the computer as it's accelerated by the electric field, as it scatters by emitting a lattice vibration or bounces off of an ionized impurity, goes off in some random direction, is accelerated by the electric field again, and either comes back out the source where it came in or goes out the drain and contributes to the drain current. So you run hundreds of thousands of those and average the results. And if I average the results, I can look at anywhere in the channel and I can say, what's the average velocity of all of those electrons? Okay. And this is what the average velocity versus position looks like. It's low down here in the source, it's low in the drain, and it pops up and is really high in the channel. Okay. If you look at these numbers, you can see, remember, one of the things we teach students in these kinds of courses is that the slope of the energy band diagram is proportional to the electric field. The electric field is highest near the drain here. If the velocity is going to saturate anywhere, it's going to saturate near the drain. But look at what's happening here. The saturated velocity, 10 to the 7th centimeters per second. The electrons are going faster than that over the entire channel. Right? They don't know anything about velocity overshoot or velocity saturation. The velocity is overshooting, we say. The reason it's happening is because in a large bulk piece of silicon, you can wait a long time and get a lot of scattering, and the velocity finally comes down and saturates. In a very short, an electron comes in from the source and zips across, and before it's had a chance to scatter more than once or twice, it's out the drain. We say the transport is quasi-ballistic. Look at this is energy versus position. Most of them are just streaming across at high energy. Near equilibrium, most of the electrons are down at the bottom of the conduction band. They're way up there. They don't have a chance to scatter enough to come down. So this velocity overshoot is something that people spend a lot of time trying to understand. It's been experimentally verified in a number of different experiments. We know that it occurs. And one of the mysteries is if the velocity does not saturate, why do the IV characteristics of the MOSFET look like the velocity saturation MOSFETs? The physics seems to be all wrong. How come it works? Okay, so we can devise this simple two-piece approximation. When you're developing the IV characteristics of the MOSFET, the complicated thing is to get a full curve that goes from small drain voltage to large drain voltage. But as we've seen, it's easy to do the small drain voltage, and it's easy to do the high drain voltage. If we could just connect the two smoothly, we'd have our IV characteristic. So we could do that with a two-piece approximation. We could say the first expression and the second expression intercept at some voltage. We'll call that VD sat. If the drain voltage is less than VD sat, we use the first expression. If it's bigger than VD sat, we use the second expression. If we're a little more careful, we can smooth that out so that it behaves reasonably and not abruptly. And we'll smooth it out so that VD sat is the range over where it makes this transition from linear to saturation. Okay, so how do we do that? All right, not so hard. This is the expression that we developed in the linear regime. Just rewrite it a little bit. Capacitance times voltage is charge. If I move the mobility, the drain voltage, and the channel length around, I can put those together as mobility times electric field. That's just the velocity. So another way to write this is the linear current is charge. Linear current per width is minus the charge times the average velocity. The average velocity is just mu times the electric field. Okay, so at high VDS, we could do the same thing. It's even easier. Cox, Vg minus Vt is charge, and Vsat is the velocity. So again, the current per unit width is just minus charge times average velocity. The average velocity is just the saturated velocity. Okay, so the current is always charge times average velocity. We just have to make the average velocity to go smoothly from what it is under low VDS to under high VDS. Then we've got a nice curve. So how do we do that? Turns out it's pretty easy to do. So you would guess whichever one of those two velocities is the slower, that's going to be the important one. That's going to limit the current. So we just compare the two velocities. If the linear velocity is slower, it means we have a small electric field and not going very fast. That's the one we'll use. If the linear velocity is higher than the saturation velocity, we say that doesn't make any sense. We'll use the saturation velocity. So if you take 1 over the average velocity and have it 1 over the low VDS velocity plus 1 over the high VDS velocity, whichever one is smaller will matter, right? The other one will be insignificant. But it will go smoothly. So you get an expression that looks like this, and it will smoothly go from one to the other. And you lump some terms together and you'll get the VD sat that we had before. Okay. All right, so we can write the average velocity as some saturation function times V sat. And that saturation function now will make it just a little more complicated, because if we give ourselves just a little more flexibility, we can fit any transistor. And so this makes it a little bit empirical. So we'll just take that and we'll raise Vd over Vd sat to some power beta, and we'll raise the whole thing to a power 1 over beta. People find that's empirical. It's reasonable, but it's empirical. You do that in almost any transistor you can fit beautifully by adjusting beta just a little bit. Okay, so here's what we have. We could look very quickly. Just take that expression, look at what happens for small VDS, small VD, much less than the saturation voltage. It just gives us this expression, and if I put that expression, multiply it by Vsat, put in the values I had for Vsat, we'll just end up with the average velocity is mu times the electric field. Just what it's supposed to be when V is small. You go through the same thing when V is high, and you'll find that saturation function goes to 1, the average velocity goes to Vsat. So it works, right? It's easy to work. Okay, so here's a model. And this is now a model that has been developed recently by some of my colleagues at MIT. So they call it the virtual source model. I'll explain why it's called virtual source later. But we just write the current as charge times velocity. The charge we can get from Cox, Vg minus Vt, or we could be more careful. We know below threshold there's a little bit of charge. That's leakage. It means we have to be a little more careful, use the exact solution or something, but we can do that. The average velocity is just this empirical saturation function times Vsat. We just have to tweak the parameter beta a little bit, and Vd sat we know. So that's a model that works really, really well. So I've just gone through the 5 parts of that model. There are only a few parameters in this model, and they all have a clear physical meaning, except this little empirical parameter there. It's not quite clear what that is. So it's a semi-empirical model. That empirical parameter, it doesn't vary very much. It's between 1.4 and 1.8, and you can fit any decent transistor. Okay, so now what we're going to find is that we can fit any transistor if we do two things. When you get to very, very short channel lengths, if you understand a little bit about transport, you say mobility doesn't really mean anything. When you're quasi-ballistic, it loses its physical meaning. That's okay. We're going to use the mobility, but we're going to just replace it by some parameter that we're going to tweak. Now it's empirical again. We're going to call it an apparent mobility, because it's not clear what mobility means in 20 nanometer channels. And this saturation velocity, as we said, we know that it's not 10 to the 7th. It's not the high field saturation velocity in the bulk. So we're just going to give it another name. We'll call it the injection velocity. And these will be two empirical parameters that we'll adjust. So it's not bad. We have this empirical parameter here, which just gives us a smooth transition from one to another. We take the textbook expressions that were developed in the 1960s and 1970s, and we just say, well, we're just going to adjust the mobility and the saturation velocity a little bit. Turns out you don't have to adjust them very much. And if you do that, boy, you just get beautiful fits to nanoscale transistors. The most recent ones that I could find were 32 nanometer technology. But, my guess is it's going to work fine to 14 nanometers. It might even work to 10 nanometers or so. Okay, so something is going on here. This very simple model, based on concepts that we don't believe should be valid anymore, still seems to describe transistors. We just tweak the parameters a little bit. So the question is, what's going on? And is there a physical interpretation to these parameters? Or are they just empirical fits? And what I'm going to try to convince you is that they're not just empirical fits. They have a clear physical reason. And there's a very good reason. These people that developed these models in the 1960s and 70s, they were really, really good. I mean, they didn't have computer simulations to guide them. They really figured out how these devices work. And they did it in a way that we can still use the basic theory with just a few tweaks. Okay, so these are the questions that I'm going to deal with in the rest of the talk. Why do these models that shouldn't work still work beautifully? The IV characteristics of a small transistor says that the velocity saturates, but that doesn't seem to make physical sense. They can't scatter enough. What are the meanings of these things, apparent mobility and injection velocity, that we have to empirically tweak a little bit to get these beautiful fits? And I'll say almost nothing about things might change below 10 nanometers. I don't know. We thought things would change below 100 nanometers. It turns out they didn't change very much. But things might change below 10 nanometers. I'll say just a little bit about that. Okay, so I'll go more quickly. That's a long introduction, but these are the things that I want to go through you with. First of all is a very simple physical picture of how a transistor works. And if you understand this, the rest of it is not so bad. So here's an energy band diagram, or here's a cross-section of a MOSFET from a few years ago. And we've been discussing in my class here that the first thing you want to do to understand a device is to draw its energy band diagram. So we're going to draw an energy band diagram from the source across the channel and out the drain and see what it looks like. So if we do that, it's easy to do. The source is N-type. Actually, it's heavily doped, so the Fermi level, it's degenerate. The Fermi level is way above the bottom of the conduction band. Same for the drain. The channel is P-type. I'm not showing the valence band down here, but the Fermi level is much closer to the valence band than it is to the conduction band. So that's what the energy band diagram looks like in equilibrium. I'm assuming I have a low gate voltage, and I'm assuming there's no voltage applied between the drain and the source, so I'm in equilibrium. There's just one Fermi level. And an electron can't flow because there's this big energy barrier that stops it from flowing from the source to the drain. Right? It's stuck. Current is zero. But we remember that if we start applying some biases, that potential energy is minus Q times electrostatic potential. So if I apply a positive potential, I can lower energies. That's how we make a transistor. So let's keep the gate voltage low, but let's raise the drain voltage high. If I raise the drain voltage high, I'm going to pull the conduction band down. I'm also going to pull, now I've got quasi-Fermi levels because I'm out of equilibrium. I'm going to pull the Fermi level in the drain, or actually the quasi-Fermi level in the drain, down also. I'm going to lower the energy of both. So if we do that, we just pull everything in the drain down. But if I have designed the MOSFET properly, if I paid a lot of attention to 2D electrostatics and short channel effects, and this is difficult to do, then the barrier that stops the current from flowing has not changed. It's still the potential on the gate that controls that barrier height. Even though we put maybe a volt here on the drain, that lower potential there wants to pull this barrier down. But if I've designed things right, the gate is going to hold it up. Right? That's why people are going to FinFETs now. Surround the channel with a gate. Have the gate control that potential energy barrier. That's a big challenge for transistor designers. So this device is off. I have a large voltage between the drain and the source, but the electrons in the source can't go anywhere. Right? So if I want to turn it on, I just apply a high gate voltage in addition to the high drain voltage. Now that's going to pull the potential in the channel down. It'll lower that barrier. The little barrier, electrons in the source can hop over it, flow out the drain, and current flows. So the device is on now. So that's really how transistors operate. Sometimes when you do the math for these IV characteristics, you do this charge Cox, Vg minus Vt, you don't appreciate what's actually going on. Where's that charge coming from? It's electrons hopping over the barrier, getting in the channel. That's where that charge is coming from. So we, if we look at the IV characteristics down here for low drain to source voltage, they look like this. Here's the conduction band in the source. The conduction band in the drain is just a little bit lower. We take the gate voltage and we make it higher, and we push the potential in the channel down. Once I've turned it on, we have more or less a constant slope. Constant slope means constant electric field. It's just VDS divided by L. Okay. If I look up here at high voltage, at high drain voltage, we pulled the potential energy down. We still have a barrier. These are actual simulations of all the 2D electrostatics and everything. This is how it really works. And, push the barrier down, now current can flow. And you can see that it doesn't really matter. If electrons hop over this barrier, it doesn't really matter what the drain voltage is anymore. They're just going to flow downhill and out the drain. You make the drain voltage higher, they flow down a bigger hill and out the drain, but it doesn't really change the current. That's why the current saturates. Right? You don't have to worry about pinch off and all this stuff that's really hard to understand and probably is not right anyway. It's really simple when you look at energy band diagrams. So to understand transistors, there are two things that we need to understand. One is the electrostatics of how you manipulate these potential energy barriers. That's what gives the transistor its IV characteristic. That's what gives it that shape that circuit designers can use and do good things with. That's what the people in the 60s got right. And our understanding of that has just been refined more and more and more, and we understand that really well. Okay. The second thing is transport. Once the electrons hop over the barrier and flow, how fast do they flow? Okay, that's where things can get complicated. Do they flow by drift diffusion? Do they flow by velocity overshoot? Do they flow quantum mechanically? We're worrying about these things more and more. Here's a simulation of electrons flowing in a device under on-state conditions. Red means there's a high electron density. You're seeing electrons come in. You're seeing some of them tunnel underneath the barrier now. That's bad. We're supposed to be turning devices on and off with the barrier. If they can tunnel right through the barrier, it's going to make it hard. You can see some of them reflecting, and we're setting up interference patterns. This is going to be the big challenge below 10 nanometers. Can you still make useful transistors when quantum mechanics says everything wants to tunnel right from the source to the drain. But for 10 nanometers or above, we can think about this classically, and it's pretty easy to understand. Okay, so now the heart of the talk here. I'm going to talk about how we would think about transistors. So if somebody had discovered a 20 nanometer transistor and invented it for the first time, and we didn't have this 50 years of history and of how we originally did it when transistors were big, we would develop an IV theory along completely different lines. It would never occur to anyone to use a drift diffusion equation for something so small. So how would you think about this MOSFET if it was just a nano device that somebody out at the Brooks Center had invented last week, and you had to analyze it? You do it in a much different way. So I want to talk about how you would think about nano devices, and then we'll map that onto a MOSFET. So this is what we think about it. There is an approach to transport. If you've taken Professor Dada's course here, you've heard about it. If you haven't, you should take his course. It's called the Landauer approach. It's a different way to think about how electrons move in small devices. So the picture is that we have a heavily doped source. It's near equilibrium, lots of scattering. We can hardly ever perturb it from equilibrium. So the electrons in that source are described by a Fermi function with a Fermi level or quasi-Fermi level that's well defined. We have another contact in the drain. It's in equilibrium too. It's heavily doped, but it might have a different Fermi level, or we'd say different quasi-Fermi level. And then we have our little device inside. This is our nano MOSFET. And we're going to characterize that device not with a mobility, because mobility really doesn't make sense at this length scale. We're going to characterize it by two parameters. One is the number of channels for current to flow, and another is the transmission. And there's a very simple expression that I'm not going to derive, but if you're going to work in this field, you'll want to understand this equation. And it says that the current is proportional to some fundamental constants times T. T is just a number between 0 and 1. It's the probability that if an electron comes in from the source, it'll transmit across and go out the drain. It's not a wave, we're thinking about particles, so it has no phase, it's just a number between 0 and 1. If it's 0.5, it means half of the electrons that come in backscatter and go back to the source. They don't get through. M is the number of channels, something like a density of states, but not quite. It's the number of channels that can carry current flow. You think about it as I-65, two-lane highway to Chicago. There are two channels that can carry cars to Chicago. There are two channels that can carry them back. Same thing here. If you have a band structure, you can figure out how many channels there are for electrons to flow in. And then it depends. There has to be a bias applied for current to flow. There has to be a difference in the Fermi functions between these two contacts. Otherwise, they're just as likely to come from the source and go out the drain as they are to come from the drain and go out the source. They'd be completely symmetrical. So it depends on the difference between the Fermi functions in those two contacts. Okay. So we haven't derived it, but it should look plausible. Okay. So I think about this as the drift diffusion equation for the 21st century. This is the equation we should start with when we talk about semiconductor physics, because you can derive the drift diffusion equation from this. Okay. But if you try to analyze a nano MOSFET with the drift diffusion equation, you just confuse yourself, because you don't know how to map those concepts onto this nano device. This was made for those nano devices too. Everything is clear when you start with this. So we have this expression. F1 and F2 are near equilibrium Fermi functions. It's just that we might have one Fermi level in the source, we might have another Fermi level in the drain. It'll be different from the Fermi level in the source if we apply a voltage and lower it, right? That's all. Okay, and as I said, you can apply this to a big semiconductor and you get something that looks familiar to us, just the drift diffusion equation. But don't go backwards. Don't try to take this and apply it to a nano device, right? That's hopeless. You'll probably get it wrong, right? Okay, so if you want to know more about this, you should read Professor Dada's book or take his course. Or you can read my book, which is just a little more applied and tries it. Professor Dada talks about this from a very fundamental perspective. In my book, I try to apply it more to problems that we might face as engineers. But as I said, if you're going to work in this field, you should make it your business to learn something about this. And it's also really, really interesting. Okay, so let's try to have a look at our nano device under small drain bias. What if we apply a small drain? So I'm going to do the same thing I did with the 1960s textbook version. First look at small voltage, then look at large voltage. Okay, small voltage, we start with this Landauer expression. We're going to apply a small voltage, so the Fermi level in this drain is just a little different from the Fermi level in the source. All right, now I have to do a little bit of math, but it'll look plausible. F1 minus F2. I could write that as Fermi function in the source minus Fermi function in the drain, divide by Q times the voltage and multiply by Q times the voltage. All right, I haven't done anything. Voltage lowers Fermi level. So when I apply a positive voltage to the drain, I lower the Fermi level in the drain, so it goes negative. So this I can recognize as the derivative of the Fermi function with respect to the Fermi energy. All right. So just a little bit of F1 minus F2 is related to a derivative of a Fermi function. Okay. Then just a little more algebra. You can see that the only difference in this formula between the Fermi level and the Fermi and the energy is a minus sign. So I could replace dF naught dEF with minus dF naught dE. Okay. Now I have a classic expression. If we plug that into the current expression, we're going to find that F1 minus F2 is a derivative of a Fermi function times the applied voltage. This should be the drain voltage here. Okay. So if I divide the current by voltage, I get conductance, and I get an expression. You read physics books, solid state physics books and things, you'll find expressions like this for the conductance of any resistor. Frequently it won't be expressed in terms of T and M, that's the Landauer terminology. If we go to 0 Kelvin, which we don't usually do as engineers working on MOSFETs, but if you were to do that, physicists like to do that, right? You can find some really interesting fundamental physics. Remember, the Fermi function changes from 1 to 0 at around the Fermi energy. If you go to T equals 0, it changes very abruptly at the Fermi energy. That derivative becomes a delta function. It's easy to integrate a delta function. So what happens is, this is a delta function centered at the Fermi energy, and that means when I do that integral, I get this beautiful expression that the conductance of a small conductor is some fundamental constants times the probability that an electron entering at the Fermi energy will make it across, times the number of channels that it can travel in. Okay. So this is a well-established experimental fact now. So back in the late 80s, early 90s, physicists were looking at this, doing experiments at 4 degrees Kelvin so that they could reduce scattering, and transmission T would be close to 1, so it would be ballistic. And what they did is they had a thin sheet of 2D conductor. This is a resistor. Here's the source, here's the drain, here's the channel. And they had a way to electrically vary the width of the channel. They did it with Schottky barriers. They just reversed biased it and depleted it so they could electrically control the width. Classically, we expect a conductor, if you make it twice as wide, you'll get twice as much conductance. It's just like having 2 resistors in parallel. What they observed when they did that was that the conductance increased in steps as they changed this voltage and increased the width. It didn't increase smoothly. It increased in steps. And those steps were 2q squared over h. Just what the theory says it should be. So this is called the quantum of conductance. So there are 2 things. One is that conductance is quantized. You can't make a resistor and get any resistance that you want. You can only get certain multiples of this quantized conductance. Now, if the resistor is a big one, you don't notice that. But if the resistor is a small one, you notice it, right? The other is, no matter how short the resistor, so we always think of the resistance being proportional to the length. No matter how short it is, its resistance, its conductance can never be higher than this. The transmission will just be 1. As it gets shorter and shorter, there's more and more probability an electron will go from the source to the drain. Once the transmission is 1, it can't get any higher. So now you keep making it shorter and shorter, the resistance doesn't get any smaller. The conductance doesn't get any higher. People have actually, I understand, taken probes and put them down on a hydrogen molecule, which is about as short as you can get, and measured its resistance. It's 1 over 2q squared over h. Right? So this is some very interesting and fundamental physics that, 25 years ago or so, we thought, well, this is interesting for physicists who are working at 4 degrees Kelvin. Now this is relevant for room temperature MOSFETs. You can measure that these days at room temperature. And if you're doing careful characterization of the MOSFETs, you worry about this now. The fact that the conductance is quantized and that the channel resistance of a MOSFET has a lower limit. You make it shorter, it's not going to get any lower. Okay, so that's the approach we're going to use when we do the MOSFET in the linear regime. When we do the MOSFET under high drain voltage, it's even easier. We go back to our fundamental expression. What's important is the difference in the Fermi functions between the two contacts. The Fermi functions are different because the Fermi level is different. If I apply a large voltage, the Fermi level in the drain is way lower than the Fermi level in the source. It means that F1 is much, much greater than F2, and we just ignore F2. It's negligible. So we have a simple expression, we just have to work out that integral. Okay, now we can do a MOSFET the way if somebody were encountering a MOSFET for the first time today, 20 nanometer channel length, and they had to analyze it, this is probably how they would think to do it. All right. I know how to treat nano devices. I'll treat my nano MOSFET this way. So we have an IV characteristic. Let's look down here. F1 and F2 are just a little bit different because we've applied a small drain voltage. Both of them are close to the equilibrium Fermi function. So the current is just the conductance times voltage, and we want to compute the conductance. Okay, a little bit of math. I'll go through it quickly because, just so you get the gist of it. You can fill in details later if you're interested. Here's our expression that we developed for small drain voltage. Now I need to know the number of channels. Well, you can figure that out. Read my book. It's not expensive, right? If you know the band structure, you can figure it out. Let's assume it's ballistic. Let's assume that it's so short that every electron that comes in from the source goes out to drain. Let's assume, we shouldn't do this, but let's do it anyway. Let's assume that we can approximate the Fermi function by a Maxwell-Boltzmann distribution because it makes life a little easier, and traditional MOS theory is usually done that way. Then we can compare to the traditional answers, and we can always go back. Then we don't have Fermi Dirac integrals to worry about. Okay, so the carrier density is just related exponentially to the difference between the Fermi energy and the conduction band. These are 2D carriers in the inversion layer, so we have a 2D effective density of states. We know all about that. Okay, so we just do the math. We do the derivative of the Fermi function in the Maxwell-Boltzmann limit. We plug everything in. It's an integral. All right. We wish it were a little easier, but it's not that difficult. You do it. Look at your integral table on Wikipedia, work out the integral, and we get an expression that looks like this. All right. I should point out, let's see. Q times the carrier density per square centimeter is just the inversion level charge. The amount of charge we have depends on the gate voltage. So now it's starting to look a little more like a MOSFET. And this collection of constants here turns out to be just the average thermal velocity of electrons randomly moving around inside a semiconductor. V sub t is the thermal velocity. Okay, so we have this expression, just like we did before. It doesn't really look like the textbook expression, but it's not too bad. It looks a little different. We'll discuss how it relates to that classic 1960s expression in a minute. But we've got an expression. This describes a ballistic MOSFET. Okay, let's do the other region. So here we're at high drain bias. We take our expression. We ignore F2 because we've applied a large bias. We just have to work out this integral. Okay, so we work out this integral. We know the same number of channels. Assume it's ballistic again. Assume Maxwell-Boltzmann statistics. The collection of constants here, this turns out to be the average velocity that thermal equilibrium electrons are moving in the plus x direction. No, the total average velocity is 0. But if you just look at the average of those moving in the positive direction, it's some finite value. Right. And here's our expression for the electron density. Okay, plug everything in, do the math, and we find that the current is charge times velocity, but the velocity is this thermal velocity. So we'll have to talk about that a little bit. So we've done that. Okay, so we have a ballistic MOSFET. We have expressions. They look different from the classic MOSFET expressions, but I'll show you that they're really not so different. We have one for the high VDS. This looks very similar. It's just that why have we replaced this high field saturation velocity with the thermal equilibrium velocity that electrons are moving around with? Right? This seems kind of mysterious. Why is that happening? Just came out of the math, but there must be some physical reason for it. Okay, so you plot the IV characteristics. You know, back when people first started looking at this surprised an awful lot of people. You know, it's a ballistic MOSFET. You know, this is just some different kind of thing. You plot the IV characteristics, it looks like any MOSFET. The reason it does is the shape of the IV characteristics comes from pushing those energy barriers up and down. Just the magnitude of the current changes, that's all. Right? So the IV characteristics look like the same. We have these expressions for the linear regime, but now we understand that no matter how short we make the channel, we can't change this slope. We're not going to make the resistance any smaller because it's ballistic. There's no channel length in this expression. And we have the expression for the on current that we have to understand a little more. Okay, so we would call that the ballistic on current. And notice, if you do this, you'll notice that the current increases linearly with gate voltage. It looks like the velocity is saturating, but the way we understand velocity saturation under high fields is it's caused by a lot of scattering. But we took all the scattering out of the analysis. We said that the probability that it will transmit from source to drain is 1. There's no scattering to bounce it back and return it to the source. So how can the velocity be saturating when there's no scattering to cause it to saturate? Well, that turns out to have a really easy answer. So these are simulations. So this is an energy band diagram under high gate voltage, so the barrier is low. And we just keep increasing the drain voltage, so we pull the conduction band and the drain down more and more, and for some reason the velocity saturates. Okay, but let's see. Let's look here at the top of this energy barrier. This turns out to be the critical place. This is what people call the virtual source. That's why that model is called the virtual source model. This is what we call the beginning of the channel. It's really what acts like the source, not this big heavily doped region back here. The charge here, if the transistor designer has done his or her job well, the charge here is Cox Vg minus Vt, just like it is in a classic MOS MOSFET, even though this thing is really small and the electrostatics is two-dimensional. If you've done things right, the charge is Cox Vg minus Vt. So then the question is, what is the velocity there? Charge times velocity is current. Now, if you look inside a semiconductor at equilibrium, you'll see electrons bouncing around in random thermal motion. They will be distributed in a Maxwellian distribution of velocities. So this is the x velocity, this is the y velocity. The xy plane is the plane of the channel. And just like an ideal gas, the gas particles bounce around, scatter off of each other randomly, and they're distributed in a Maxwellian velocity distribution. That's what this is, a Maxwellian velocity distribution. Okay. But it's kind of interesting. Maxwellian velocity distributions are produced when you have a lot of scattering so that everything comes to equilibrium. Then you get a Maxwellian velocity distribution. There is no scattering here. How can we get a Maxwellian velocity distribution when we apply 0 volts between the drain and the source? The answer is very interesting. We're assuming that this source is a very big region with lots of scattering. There is a Maxwellian velocity distribution there. Same thing for the drain. The positive half of those electrons can hop over the barrier and get into the channel. The positive half, all of the positive x velocities in this came from the source. The negative half, the drain, they're also distributed in a Maxwellian velocity distribution. The negative velocity ones can get into the channel and come back here. The negative half of this came from the drain. So scattering did produce this equilibrium distribution, but it was scattering in the source that produced the positive half. It was scattering in the drain that produced the negative half. Okay. Now you apply a little bit of gate voltage or drain voltage. You lower the Fermi energy, you lower the conduction band in the drain. Okay. No problem. The positive half can still come in. It's just like it was before. Okay. The negative half, though, has to hop over a bigger barrier to get here to the virtual source. That means fewer of them are going to be able to hop over. The negative half is smaller. That means the average velocity now is bigger than 0. Current is flowing. Right? You apply a larger drain voltage, even larger. You've got an even smaller negative half because there's an even bigger barrier. You apply an even larger one, and now no electrons from the drain can hop over and get into the channel. You only have the positive half that came in here. The average velocity of that positive half is the thermal equilibrium velocity that they were zipping around in the source, and they just hopped over that barrier and came in. That's the biggest that the velocity can be. The velocity has now saturated because it can't get any bigger now because you only have the positive half coming over the same barrier. But the velocity has not saturated where the textbooks say it would saturate. It's not saturated in the drain end where the electric field is high. It's saturated at the top of the barrier where the slope is 0. It's saturating where the electric field is 0 because of this mechanism. All right. So that's really interesting. So the early transistor pioneers had it right. The velocity is saturating in these devices. It's just it's saturating for a completely different reason than it was 40 years ago. But it's still saturating. And that's why the characteristics still look good. So that explains, several years ago, everybody was focused on this, thinking, wow, this is wonderful. We make transistors shorter and shorter. The velocity just gets higher and higher. Well, it turns out that if you make the drain voltage bigger and bigger, the velocity at this point saturates. It doesn't get higher and higher. Now, it's bigger than 1 times 10 to the 7th. So that has to do with Fermi-Dirac statistics and things like that. That's why it's bigger than 10 to the 7th. It's the thermal velocity with Fermi-Dirac statistics. Right. Okay, so just very quickly, you look at this and you say, does this have any relevance to modern transistors? So just compute this ballistic theory. Those are the red lines. Compare it with measured characteristics. What you typically find these days in a silicon MOSFET, that the devices operate at about half of the ballistic limit. They give you half of the current that you would get if you had no scattering in the channel and the transmission was 1. That's actually pretty close. Okay. It's actually 20% down here, but it's 60% up there. All right. So that's where we are in MOSFETs. It's actually interesting. We've been there for about, for about 15 years. And you think, well, if I make the channel shorter, I should get closer to the ballistic limit because there'll be more chance they can go across and not scatter. That's true. But if you just make the channel shorter, your transistor won't be very good. Then you'll go back and you'll raise the channel doping and you'll control the 2D electrostatics and do everything that you need to do in order to make the transistor behave properly, and you'll find you're back to 50%. That's where people have been stuck. They haven't found a way to get past that. There are transistors, however, that operate essentially at the ballistic limit. If you look at 3-5 transistors made on high mobility semiconductors, and you do the same kind of comparison between the ballistic theory and the measured characteristic, you can see that a transistor like that operates almost at the ballistic limit. You know, nothing like what a textbook would say it operates at. So these things can become very, very important. Okay, so if we're going to understand this, I need to say a little bit about scattering. So scattering is where things get complicated. I teach a course, EE 656. If you're interested in this, you can find it on the web, or you can take the course and you can learn all these details about scattering. But the concepts that we need are relatively simple. Let's think about our channel as being a slab of material of some length L. Some electrons are coming in from the source. Let's say the magnitude is 1. What we want to know is the fraction of them that come out the other side. And that fraction is t, a number between 0 and 1. And you can see, there's a very simple expression, and you can see that this works. If the channel length is much less than the average distance between scattering events, this expression is going to go to 1. Right? Makes physical sense. If the channel length is much longer than the average distance between scattering events, this is going to get very small. There'll be many opportunities to scatter and turn around. All right. It's actually better than that. It's not just empirical ad hoc thing. You can actually derive it, and it works really well in practice. Okay. So this critical parameter is the average distance between scattering events. Okay, so we want to get this in our theory so that we can treat MOSFETs that operate when there's a little bit of scattering. You might think that, well, all we have to do is to multiply the expressions we got before by this number between 0 and 1. Turns out it's a little more complicated. Down here in the linear regime, that's all you have to do. You just multiply it by the transmission. If you can figure out the transmission, you're home free. Up here at a high drain voltage, it's a little more complicated. You don't multiply it by T, you multiply it by T divided by 2 minus T. All right, that's a little mysterious. But let me do this very quickly, because if you don't follow it, that's okay, but you sort of get the gist of why it happens. The charge at the top of the barrier, current is charge times velocity. So if I want the charge, it's the ballistic current that's injected divided by the ballistic velocity. There's this width I have to worry about too. So that would be the amount of charge under ballistic conditions. When I'm not ballistic, then I have a stream. I have some carriers with positive velocities. I have some carriers with negative velocities. I have to add the two up in order to get all of the charge. This is the stream with positive velocities. If T of them are transmitted across, then 1 minus T come back in the other direction. So this is the stream of electrons in the negative velocity. They travel at the same thermal velocity, so I can get the total charge. Okay. Now, when I have scattering, I'm going to inject some fixed amount. I'm going to inject some amount I plus into, and the key thing here now is that the key thing is MOS electrostatics. If I've designed my transistor properly, charge is Cox Vg minus Vt. It doesn't matter whether it's ballistic or whether it's diffusive. That's just electrostatics. So I equate the ballistic expression to the expression with scattering. And what I'm going to find is that when I have scattering, I'll inject fewer electrons because I'm going to get some charge contributed from the ones with negative electrons. So when I maintain that, when I say that the charge always has to be given by MOS electrostatics, whether there's scattering or not, that's where this 2 minus T comes in. And then what goes out is T times what came in. So now I've got my T over 2 minus T. So the point just is that you have to understand MOS electrostatics in order to get this expression right. And that becomes important at high drain voltages. Now, one of the things that you'll find is that if you compute the transmission at low drain bias, it's about 20%. if you compute the transmission under high drain bias, you'll find that it's much bigger. About 70% of them go across in a silicon MOSFET. That's a little mysterious. Higher voltages should give the carriers more energy. They should be more likely to scatter. If anything, it should be less ballistic under high bias than under low bias. But that's not what you find when you analyze measured data. And how do we understand that? So this is the way I understand it. Here's our energy band diagram under low drain bias. We have an expression for transmission, mean free path divided by mean free path plus channel length. If an electron that comes in, if it scatters anywhere inside that channel, it has a chance to turn around and go back out the source and not give us any drain current. Okay. Now what happens if you apply a high drain bias? You pull everything down. Right? The gate tries to hold it up. Okay, now we have a short region here, right around the virtual source, the top of the barrier. If electrons scatter there, they can return to the drain. If electrons hop over that and start going down the electric field, it doesn't matter if they scatter anymore. It's irrelevant. The electric field is so strong, it'll turn them around and sweep them out. It's like the collector of a bipolar transistor. It's just going to sweep everything out. The only scattering that matters is the scattering that occurs in this thin, short, low field region right near the beginning of the channel. So, the way we understand that is just that the region that controls the current is just a tiny fraction of the channel length. And that means even though the mean free path hasn't changed, that length has changed. So the probability that they'll transmit is much, much higher. So this region is a bottleneck for current flow. Okay, so we're almost there. So I want to pull this all together. You know, I'm not going to be able to say much about what happens below 10 nanometers because that's a current research and technology challenge. But we've seen how you would think about this device as a nano device. It looks quite a bit different from, except for the electrostatics, it looks quite a bit different from the traditional way that is in every textbook. But I want to try to connect those now, and you'll see that they're not so different. And we want to try to, in the process, understand why we can still use these models from the 1960s and just make a couple of tweaks, and they still work beautifully. Okay. All right, so here's the expression that we've developed. You know, there's no mobility or anything. It looks completely different. But we know that the transmission is related to mean free path. And I have to pull out a little transport theory. The diffusion coefficient is also related to mean free path. So you may remember what the units of diffusion coefficient are? Centimeters squared per second. So actually you can show with some transport theory that diffusion is random thermal motion. So it's the thermal velocity times the mean free path divided by 2. That's the diffusion coefficient. If I've got the diffusion coefficient, the Einstein relation gives me the mobility. I just do a little bit of math and I rewrite this, trying to get the mobility into it. And if you do that, something really interesting works out. You lump everything together, and there are some terms that we can lump together and we can call the apparent mobility. And there is this rule that we've seen before. It looks like Mathiassen's rule. It looks like we're adding two different mechanisms. And one is the real mobility. This is the effective mobility of electrons in the channel. And the other one is something that we call the ballistic mobility. And what is that ballistic mobility? Well, when you lump all of these parameters together, it's not surprising that the mobility depends on the average distance between scattering events. All right, that makes physical sense. The more scattering, the less that distance is, the smaller the mobility is. That makes perfect sense. That's a real mobility. This ballistic mobility, you just replace the actual mean free path by the channel length. Now, when electrons travel ballistically from the source to the drain, they scatter a lot in the source. They zip across the channel and they don't scatter. They scatter a lot in the drain as soon as they get there. So the average distance between scattering events when it's ballistic in the channel is the channel length. So that's what this ballistic mobility is. You take this expression, you get our ballistic theory, everything works out beautifully. You just have to replace the real mobility by this apparent mobility, and it's not empirical. There's good physics behind it, right? People measure this these days. How about high VDS? Same kind of thing. This expression looks quite a bit different. We've seen that under saturation conditions, T is mean free path over mean free path divided by the length of this bottleneck regime. We also have the diffusion coefficient. Rewrite this a little bit, and we find that the saturation current is charge times velocity, and the velocity is given by an expression like that. And let's see if we can make sense out of that. That average velocity is 1 over the thermal velocity. This is what they get injected at from the source. This is what they would travel across if it's ballistic. D over L. D has the units of centimeters squared per second. L is centimeters. This is a velocity. This is the average velocity that electrons are diffusing across a region of length L. That's how we interpret it. So what this expression says is that the velocity up here at the virtual source is the slower of two velocities. If electrons have to diffuse across that, then that's the velocity. If this velocity gets bigger than the thermal velocity, then we say that doesn't make any sense. Diffusion is random thermal motion. You can't diffuse faster than the thermal velocity. Then it's the thermal velocity that limits us, right? That's the ballistic limit. So the picture is that under high drain bias, the current isn't a drift current, it's a diffusion current. This bottleneck region looks just like the base of a bipolar transistor. Electrons get injected to this region, they have to diffuse across. Once they get across, they see the high field part of the channel, which is just like the collector of a bipolar transistor. It sweeps it across. This is a really useful way to think about these small devices. And it's not a new idea, but not many people have paid attention to it. You know, this fellow Ed Johnson back in 1973 pointed out, we think about a MOSFET and a bipolar transistor as being two different devices. Draw the energy band diagram, it's really the same device, right? Okay, so we have these expressions, and we see that we can easily take these expressions and convert them into proper expressions that are physically valid. There's actually, it turns out there are two ways that you can compute the tradition, you can correct the traditional expression just by rearranging the math. You can either replace the channel length by channel length plus 1 mean free path. Then as your channel length goes to 0, you don't have to worry about things blowing up. It goes to the proper ballistic limit. Or you can replace the mobility by this expression involving the apparent mobility. And, you know, we have a physical interpretation of what this velocity on Vsat is. It's just the velocity that they're getting across the bottleneck region at. And it can't ever be faster than the ballistic, than the thermal diffusion velocity. They get injected at the source. If they don't scatter, they can't get past at a velocity that's any higher than that. Okay, so that's pretty much the picture. And it's really relatively simple. But I want to talk about, some of you will go out and do technology development, and you'll see if you can push the technology to 5 nanometers. You know, people have done that. You know, we thought we'd never get below 100. It was impossible, right? But bright students graduated, they went out and figured out a way to do it. You guys will figure out a way to get below 10 nanometers, right? But what's the challenge? So the challenge is this. These are quantum mechanical calculations. So here's the conduction band profile, and this is energy, and this is the magnitude of the current. Red means lots of current flowing. So this is a device that's supposed to be off, 13 nanometer channel length. You can see where the current is flowing, over the top of the barrier. This is the way a transistor is supposed to work. Push the barrier down, more current will flow over the top, you'll get more current. You go to 10 nanometers, you can start to see a little bit of tunneling, but it's not too bad. 10 nanometers, the picture I outlined still works just fine. You go to 7 nanometers, and now you start to worry. There seems to be quite a bit of it tunneling underneath. You go to 4 nanometers, the electrons don't know there's a barrier there. They just tunnel right through it. This is going to be a problem. You know, can you do anything about it? You know, well, maybe. Now I'll just point out, My colleague Gerhard Klimek has a student, Sumitra, who's trying to figure out if you can do better. And these are energy band diagrams, and I'll just quickly point out the punchline for his work. Depending on what orientation you use for the channel and what strain you put in the silicon in the channel, you can get different effective masses. Remember, tunneling, a light mass tunnels very effectively, a heavy mass doesn't. If you can arrange things so that you make the silicon effective mass heavier, it'll be harder to tunnel. And that's what he's showing here. If you do things with orientation and strain just right, you can get most of the current to go over the top of the barrier, and you can make a 5 nanometer channel length that works like a transistor is supposed to work. So there's hope. Right? It's not going to be easy, but there's hope. Okay, so just to summarize, this is it. This is what you should take away from this lecture. Here's how we think about how a small transistor works. We have this energy band diagram. We focus on the top of the barrier or the virtual source. There we know that the current is charge times velocity. The charge is just given by classic MOS theory. If you design the transistor properly, which is really, really hard, right? This is why people are doing FinFETs right now. This region, if it's designed properly, is strongly controlled by the gate, but weakly controlled by the drain. You add drain voltage, you pull the energy down here. Hopefully you don't pull the barrier down. Then you've got a good transistor, and the current is saturated. So if it's a well-tempered MOSFET, then the energy barrier is mostly controlled by the gate. And then there's this bottleneck, this little region here. So the magnitude of the current is controlled by, can electrons get across that bottleneck without scattering and turning around and going back to the source. And we've explained why this model works so beautifully, why we just have to take the traditional model of many years ago, replace the mobility by an apparent mobility, reinterpret what this saturation velocity is, and we're not just doing ad hoc curve fitting, right? It's based on sound physical principles, and it all makes a good deal of sense. So I've tried to, explain that understanding MOSFETs, really maybe the most important part is electrostatics. The hardest part to understand is transport. But we described how if you use this Landauer approach, you can get a simple, clear physical approach to understanding that. It's not too difficult. What happens below 10 nanometers is still uncharted territory. Things seem to be getting more complicated there. We'll have to figure out how to handle that if we want to keep Moore's law going for another 20 years. Okay, so if there are questions, I'll be happy to take them. This talk is going to be available as soon as we get done with the production on NanoHub. And if you really want to know how this all works out carefully, take my short course. If you wait a few weeks, it's going to be free. If you sign up tomorrow, you have to pay $30. But it's well worth $30. Okay, so thanks for listening. And this sort of, for my class here at Purdue, this kind of wraps up the picture of MOS, what it is that we've been talking about all along. And I hope for the audience in Mexico that this convinces you that there's a simple, clear, physical way to think about these devices. And if you have any questions, please ask. Thank you.